Hi everyone, welcome to our IEEE Big Data Analytics Tutorial Series. This is Qiu from Arizona State University. Today we are honored to have Mr. Antoine Marot from RTE France to be our monthly speaker. He's going to talk about how to learn to run a power network in a sustainable world. This tutorial will focus on the RTE computation and the problem definition. So let me give a brief introduction of Mr. Marot. Antoine Marot is the lead AI scientist at RTE. He owns a double master degree in engineering from Paris Central Tech Engineering School and also Stanford University. After entering at Tesla Motors, he joined RTE R&D on the Topology project 6 years ago with the long-term goal to develop a personal assistant for control room operators with AI. Through collaboration with INTRA, the French AI research lab, he supervised several Ph.D. students on augmented power system simulators with AI and on human intelligent machine interactions with a strong focus on interoperability. He recently co-authored several papers using AI for power systems and gave different talks on topics such as IGCNN AI conference keynote. He advocates for a new AI for power system community, bringing together researchers from both fields to accelerate the application of AI. The Learning to Run Power Network Challenge, which will run along NEURIPS 2020, the largest AI conference, is a strong step forward towards it. So this tutorial will be about 60 minutes long. In the end, we will organize the Q&A. During the talk, if you have any questions, please feel free to send them to me through the chat box. Okay, now without further ado, I will give the speaker to Mr. Marot. He will give you a talk.
Yeah, thank you very much for the introduction. Hello, everyone. I'm very happy to be here to talk about this project. And thank you to the IEEE Big Data webinar team for hosting me today. So, as we just said, I will be talking about this Learning to Run a Power Network Challenge. We already had some competitions on this topic, and right now we're hosting the biggest competition so far at NeurIPS, so the biggest conference in AI, and I will be talking about it a bit more. But let me give you a bit of introduction and motivation for this project we had. So I'm sure you know it, but AI is booming. It's been about 10 years now. There's been this ImageNet key moment where suddenly we saw a great increase and a great breakthrough in performance with AI, and especially deep learning and neural networks. And also lately in natural language processing, we've seen quite incredible progress as well. And the keys of success for this breakthrough and revival of AI are mainly due to large benchmarks and the capacity, the ability to leverage big data, the ability to leverage computation, the availability of open source platforms and also open source papers and code, and also the deep learning revival. And one thing maybe to note is it's not much due to new algorithms and theory yet. It mostly relies on many developments in the late 90s, but since then it's been mostly due to those elements I just quoted. And just for a few numbers, you can see this curve at Google, where over the years you have an exponential increase in the use of deep learning in every application they have. So it's quite striking. So AI based on deep learning is starting to impact many fields and layers of society at a fast pace, and I think we should be aware of that for sure. At the same time, electricity and power grids, power systems, they've been, I mean, great engineering breakthrough in the early 20th century, and I mean, it's been a real revolution. But we can wonder if all the problems are already solved, or are there any other matter to deal with? And maybe you know this this professor and very well-known researcher Andrew Ng from Stanford University. So he has this phrase: "Artificial intelligence is the new electricity." So it feels to us like we're getting a bit old, you know, because he's talking about new electricity. But there are actually quite a connection between the impact of artificial intelligence today across society and what was the impact of electricity in the last century. And maybe what's interesting will be to see how we can somehow take the best of both worlds to design the new smart grids of tomorrow. But the question, yes, is, are blackouts a story of the past? And so I like to give this little quiz just so that we have a sense of what it means today to operate a power grid in a control room. So the question is the following. So how much time a grid on average could run without human intervention? So you have 4 answers here. Is that a minute? Is that an hour? Is that up to the next storm? Or can it run automatically forever? So I leave you 10 seconds to just think through it. So the answer is rather an hour. So it doesn't mean if you can leave, you know, a power grid today operates without any intervention for an hour for sure. But on average, you can somehow wait a bit for an hour. But a minute for sure is too short for human intervention. So we have automation on the grid that deal for that. And for sure, if you have a big storm on the grid, it can damage a lot the grid, and then we have some exceptional measures to intervene. But the key message here is that today we really need human operators to operate the grid. It's not, I mean, you know it. Electricity is not delivered kind of magically to your home. There's still a lot of work behind. And so here, basically, you see a control room today, a very typical control room today. It's quite a complex work environment, actually. There's those big desks with many information and applications, many screens, actually. So yeah, it doesn't seem very easy, but somehow, maybe, you know, with AI, we could make things a bit smoother and better, because why do you need so many screens, basically, when today we're all using a smartphone with a lot of information inside it with some assistance. So yeah, we have this project at RT Apogee, which goal is to really rethink a bit this ecosystem of applications for the operator and bring a new assistant interface. The other problem, you know, is that everything is getting also more complex. Basically, there's this system we have to consider now, Earth, because of climate change and our impact on the climate. And what we want to do is basically reduce our fossil fuel usage and avoid using too many resources and expanding too much a grid. And at the same time, we like to integrate more renewables and maybe use more AI, to have more flexibility on the grid while we get some more constraints. So sustainability is a key, and future smart grids, they will have to do better, but with less. So somehow that's where AI comes in. And so we can wonder if AI will be the 21st century achievement. Yet, actually, power systems are still the most complex artificial system on Earth. They're so wide with so many automatons. But for sure, AI is making a great impact today, and we have to think through that. So how AI can be of any help here? And so if you remember well, one key of success of AI today is the availability of large benchmarks and data sets. So we think we're missing actually in the power system community such a benchmark to actually test the potential of AI to serve power systems. So that's kind of the goal of our whole project here for the Learning to Run a Power Network challenge. We want to test the potential of AI to robustly operate the power grid in real time given some operational constraints. And somehow you can see that similar to AlphaGo. You can imagine kind of an artificial agent trying to take some decision. So you could think of that as AlphaGrid. But the idea is not to replace the operators, in the short term. It's more to test the potential of AI to make some smart suggestions to the operators. And as you know, on the grid, we have different kind of flexibilities. One great flexibility actually is the topology of the grid, because we can switch breakers, we can do some branch switching, we can merge electrical nodes or split them. And so the topology is everywhere on the grid, basically. So it's a great flexibility. We also have some power devices that are quite interesting. So transformers, phase shifter, some high voltage DC current lines. And for sure, you can control the productions and the loads if you like. But the thing here is that we've seen a lot of research on redispatching and load shedding, for instance, but those are quite expensive. Why we've seen very little research on topology and some research on power devices flexibility. So we really wanted here to put the spotlight on this flexibility that is underutilized today, the topology flexibility. But it's a very hard problem because it's combinatorial, it's nonlinear. So that's why we think also new method that comes from AI community can help us make some breakthroughs there as well. And the motivation for a challenge are several. So it's a way for us to exhibit important real-world problems to the research community. So basically today, the AI community is also making a lot of work on video games, for instance, but I mean, it should be of usage, for the real world. Otherwise, it's not very impactful. It's also a way to develop a large benchmark for reproducible science. So basically, as the organizer, we're modeling a problem, designing it, and we're asking anyone to help us solve that problem by participating in the competitions. So we kind of decouple, the modeling from the solver. And then we'd like to attract new communities, especially the AI community, through an easy-to-use platform and a gamified problem. Because since I've been working at RT for the power systems, I've kind of this feeling that the power system community and the AI community are two very distinct communities that don't talk a lot to each other. but they're very rich, and I think, if you're attending this webinar today, I think we all think it will be worth it if they can work together and come with new approaches. So that's kind of the goal of this project as well, to help have this new kind of community of AI for smart grids. So let me come now to some elements about the challenge overview. So what this is all about. So it started with this competition last year. It was rather a small one. In 2019, we had about 100 participants, and the duration was about 6 weeks. So the participants, they came both from the power system and the machine learning AI community from all around the world. And actually, to get the prize, the winning team had to open source their code to share it with anyone, so that we make advances, in the research community, and it benefits to everyone. So that was quite already an experience. And the idea behind that came from actually some previous competitions at NeurITS, Learning to Run. So this competition was about learning to have an exoskeleton walk and run, which is not that easy actually. So how do you build such a smart controller? So those people, they were biomechanical engineers and researchers at Stanford. And what they had this simulator with a great model of the body and of an exoskeleton. But they could not really have it work. So they had to ask other people to help them design a smart controller. And how they did that, they basically opened their simulator, they made it accessible through Python, through an API, so that you can call the simulator and play with it. Then they design a game, basically, so a game environment in which to test the controller. And this was all encapsulated in this now very well-known GIM OpenAI framework, which is used a lot for reinforcement learning today, but also other kind of control approach. And basically what they ask then, that's where AI comes in. It's a link between the reality, the environment, and the controller. So they ask the participant to help them make that link possible and design a smart controller based on that. So basically, we took the same kind of approach for our project here. And so we have this ecosystem now available, which mostly relies on this framework, Grid to Operate. So it's actually a test-bed platform in which we model real-time operation. We can run controllers that manage power grid, and we'd like to benchmark control algorithms for that. So it's basically the architecture you just previously saw. So you have a simulator that you can call. You model an environment, and you use OpenAI GIM behind it. But then you have to provide data. So we have this module, which is called Chronics to Grid, which generates a realistic power grid time series. Then we have this repository where we want most people to share their approaches so that it benefits to everyone. So you already have some baselines there and some agents you can use for yourself. And then once you have data and an agent, you will try to learn the best agent possible by running it through the Grid to Operate framework. And at the end, you can analyze the behavior of your agents through this GUI, which is called Grid to Viz. And it's very, very handy to understand what happened, why an agent took such an action, because of which context, and etc. So I encourage you to look at those different modules, which make this whole project possible, and I would say fun also for everybody. So if we go back on the modelization of our problem here, so here on the left, you see a typical schematic of reinforcement learning problem. So reinforcement learning problem, it considers that your controller is an agent that can interact with an environment by doing some actions. And then it gets some feedbacks on how good its action was basically on the environment. And it gets an updated observation of the state of the grid, basically. So here for our problem, you can see observations as the power flows on the grid, the productions, the consumptions, the topology, and also the month, the day, or the hour. As an action here, we mostly focused at first on the topology. So you were allowed to connect or disconnect a transmission line, or you could change the electrical configuration within a substation, as you can see on the schematic below. So on the figure, you start at time t with an overload on some given line. So you will get a negative reward. So basically a negative signal for that because you're not safe. And then you can take an action, which is a node splitting action here, which will redispatch the flows basically and help you get back into safety because you don't have an overload anymore, and then you get a positive reward. So your agents will iterate over many scenarios, trying some different actions, and at the end it will converge with the actions that get the best reward. And hopefully it will become robust to overloads and blackouts. And so as organizers, so the participants, they can learn their own agents or design their own expert agent, for instance, on their own. But then we want to test them on some specific conditions. So what we want basically is to minimize the cost of operating the grid. So we take into consideration at each time step, what is the cost of the grid operation at this time, considering the energy losses on the grid and the cost of redispatching action. But there is also a cost for sure if you get into a blackout, which is quite high. It depends basically on the load you cannot supply. And then the overall cost over a scenario, an episode, is the sum of the cost of operations while you don't have a blackout. And if at some time step t end here, you have a blackout, then so for the remaining of the scenario, you will have the cost of a blackout. And then to get a score, we test the participants on some episodes, and we sum the score over every episode. So scenarios. So mainly participants, they're tested on about 10 to 20 scenarios of different difficulties with a duration between 3 to 7 days. And the time resolution here is 5 minutes. So every 5 minutes, you have a new observation and you have to take a decision. So we come now to what's behind. So how did we made such a model of real-time operation? So we had some requirements for sure to have a good challenge here. So we want this to be representative of the reality, so to be realistic, to represent real-world characteristics. Want this to be interesting, so the agents should take some diverse actions in diverse contexts to control the game. and it should be feasible. So you should have solutions to avoid blackouts or game overs. And so in our problem here, the main parameters are the line capacities. So yeah. Is there a question? So yes. the line, yeah.
If you want to take some questions now, there is a question. There are two questions for now. Mm-hmm. So, are you aware of what power system applications where deep reinforcement learning has been applied?
Yeah, sure. So we actually have many papers already using deep learning. So mainly you can accelerate the computation of simulators. So you can develop proxies of simulators. And you can also, I mean, basically find some help assist the operator by giving him some better information. So it's more about human-machine collaboration and interactions. So what is a good context to make a decision? What kind of atypical situations you can get through and you can find in your historical data set, basically. So, I mean, yeah, there are several applications to deep learning. And here we are talking about using deep learning, but not only deep learning. I mean, it's up to the participants to develop some new controllers.
Mm-hmm. Yeah, the next question is, how do you consider the impact of switching on N-1 contingency protection?
So actually, so we have two competitions running at so two tracks of our competition running at NERDS, and one track is about robustness. So you will see later, but basically you have an adversary, an opponent that will disconnect the lines, and you don't know that beforehand. So basically that's how we'll test the robustness of agents towards N-1.
Yeah, so, yeah, I think, yeah, let's move on. I will keep the following two questions later, maybe.
Okay.
Yeah.
Thank you.
Yeah.
So among those requirements, there is a trade-off, between how interesting is your problem or how difficult it is and how feasible it is. So you have to assess that before releasing the problem. Oh, sorry. That's I still have and so for realism, so basically we try to generate realistic time series. So here you can see some time series from solar, from wind, from nuclear in red, and from thermal production. Then you have to know where to localize, your power plant. So for sure, it makes more sense to have big capacities on the transmission grid and smaller capacities as solar power plants on the distribution grid. And then you have an environment in which to operate a power grid. So here it was IEEE 14 grid on which we made the first challenge. And there is a PSCC, so Power System for Control conference paper about that, if you're interested. And then how do we set the thermal capacities of the power line so that it looks realistic as well? So for sure, we want to see some power lines that get overloaded some time of the year. So we choose basically the lines we would like to see overloaded, and we set the thermal limit so that they're overloaded for some time of the year. For the other lines, we choose the line capacity to be above the max flow with some ratio. But what makes the game interesting are actually operational constraints. And in reality, the control room operators, they have a limited time, to intervene. So basically, they have 5 to 10 minutes to take 1 or 2 actions on the grid before the line disconnects, given some protections on the grid, because then there's a high risk of security for people around the line. Also, so they're limited the number of simultaneous actions they can do. So you don't want to perturbate too much the grid at the same time. And once you do an action, you have some cooldown time you have to consider before you can reuse an asset. So you can replay with a breaker. So there is really a budget associated to the actions you take. So you better pick them. You better have to pick them carefully. And for sure, an agent that would do random actions will fail very, very quickly. So yeah, we started with this IEEE 14 grid because it's a minimal grid in which we can play with topology because it's sufficiently meshed. But I mean, it's not a big grid, so you could run into infeasibilities. For instance, if those 2 corridors were overloaded at the same time, basically you have no solution to redispatch the flows on one side of the grid or the other. So you have to be aware of that. And to test the contextual feasibility of our problem, we run some simple baselines that managed to solve a good percentage of the overloads, but yet there were still many overloads that we could not solve with those baselines. So there was clearly a challenge there for the participants. And then we cherry pick our scenarios on which we test the participants. So we have some easy scenarios. So it's basically to test that the agent is not doing some random things. So it's basically scenarios during which a lazy agent, so an agent that do nothing, finish the scenario. Then we had some medium scenarios where this do nothing agent fails, but our baseline could solve those scenarios. And then we had some remaining hard scenarios that we could not solve yet with our baselines, and which will basically allow the best teams to win the challenge. And learning to run a power network is actually a series of competition now. So we started with this small IEEE 14 grid last year. We already had a new competition this year on 1/3 of the IEEE 118 grid. And we introduced redispatching actions then, and also some maintenance on the grid. But those are known in advance, and they're planned. And now we're running those 2 tracks for the NeurIPS competition, so in a sustainable world. So the first track, we just said the word previously, it's about robustness. So you have an attackant that will disconnect some lines, and the agent will have to be robust to that. And then we have this track, adaptability. So it's really about sustainability. So we want an agent to be to adapt, to new energy mix where we have a lot more renewables. So the same agent should be able to operate the grid today, but also still manage to operate the grid tomorrow. And for that, we're very very happy and thankful to our sponsors and collaborators. So we actually collaborated with EPRI and also with some AI organizations such as Google Research, University College of London, as well as Lab 41 in the US. And so we had many contributors to design the problem here. So yeah, really thank you to everyone. And we have some materials available. So we have this website where you will find the main informations and any news and materials that will help you get into the problem. So basically, you can see a white paper about reinforcement learning for power grid operations. You can see the description of the current competition at Marot, and you can find the PSCC L2RPN 2019 paper. And then you have some starting kits to help you start with small examples and use the framework we have. And then you're good to start designing your agent, basically. We have a great documentation of the framework if you want to use some more advanced feature. So really take a look at it, and we think it will be very handy to you. But we welcome also a lot of feedback. We have a Discord channel, so a forum in which we reply a lot, and we consider any questions that is asked. So yeah, just a few words about the 2019 first challenge we had. So the best team were actually two teams working at the interface of machine learning and power systems. So the winning team was Gerina, which is a subsidiary of State Grid of China in Silicon Valley. And the second team was a team of Ph.D. students at Iowa State University, as well as Arizona State, I think, University. And they both used some reinforcement learning approaches, but with some expert rules as well. So you can see the explanatory videos of their winning approaches on this link, if you're curious. And here you actually see over a scenario how the different kind of agents behaved. So DQN and A3C were actually the winning approaches using deep reinforcement learning. Then we had also an expert system here. And so what you can see is that on this axis you have time, and you had actually two overloads across the scenario if you did nothing, in which you will get a game over. So actually, the winning approaches, they anticipate quite soon the overloads, and probably they get some margin, but they learn that. While the expert system actually runs many actions, and at some point is kind of lost among what should be the best action. So it kind of oscillates between actions, and it could not succeed at every scenario. So yeah, expert systems in this competition, they tried a lot more instantaneous actions, while learning agents, they took less actions, but with more anticipation. So overall in this competition, learning agents showed to be more robust, but expert systems are still interesting also. And so also in terms of computation time, in terms of score, basically the expert systems, they did a lot more simulations to find a good action, while the deep reinforcement learning, they basically could select just very few actions. They actually simulated those actions to be sure they will be effective, but they were running a lot faster than expert system approaches and also OPF approaches. But then we wonder, if what they did they solve the problem, or do we still have some margin from improvement? And so we designed a new baseline, which is an oracle. So this baseline actually sees the future. A scenario is deterministic for it, and tries to find the best course of action for this deterministic scenario. And then you can see how far from the oracle the different agents were. So basically, I mean, they were still, let's say, about 60 to 70 over 100 So they were reaching this kind of score, but for sure there was still room for improvement. And basically, they mostly tried to be robust, to overload, but they didn't learn to optimize the flows and the losses continuously. And so the best model from last year, actually, they are now open source on this repository, so L2RPM baseline. So you can actually use these models and retrain them on a new problem if you like. So it should help some people start a bit more easily on the problem and actually get some interesting results. And just some few words about the recent competition we had, which just finished about a month ago. So what was interesting there is that the top participants, they were not actually from the power system world. They were basically, from Beidou or the equivalent of Google in South Korea. So basically, they didn't really understand at first what was the power system and how you can operate it. But I mean, for sure, they have a lot of experience with AI. And so they made some very impressive results there. There was also some people, so the third ranking participant and the fourth ranking participant, they were at the interface of machine learning and power system. And if we look at the best results of the winning team, so basically they succeed to finish every scenario on which they were tested on. But they did not, again, optimize the flows continuously, so the energy losses. You can see that because they didn't get a lot more than 8/10 on every scenarios. Basically, there were 2 points if you were managing the losses. And so if we look at a case, interesting case where you have an overload and the agent actually takes some actions. So actually they used kind of a risky strategy because they were switching on and off some lines. So what was impressive is that they learned this strategy. It was kind of a little hack, I would say, in this problem that we actually fixed from them. But yet, yes, they were circling around the overload so that they could get some time so that the overload disappeared. And their agents actually learned some very interesting topologies at different substations. And when you look at the combinations of those topologies, they're actually quite robust. So they made a video of their approach. So you can see that on our competition website. So what they thought would be the main challenges was that the action space, so the number of topology configurations and actions you can have is tremendous. It's over 100,000 in dimension on this problem. So for sure, you have to be smart on how you explore such a huge action space. And so what they did, but you can get some more details in their video, they use a graph neural network. A graph neural network basically helps you take into account the grid topology and many informations about the loads and the productions. And they also formulate the problem a bit differently. So they don't try to switch one breaker or the other. What they try to reach is rather a desirable topology configuration. So it's actually, the dimension is a lot less then, but it's actually harder to have some reinforcement learning approach to do that. And once they have a desirable topology configuration to reach, they will pass some execution orders to the different substation in a sequence. And here you see their model, so their deep learning models they use. So they use some graph neural network. They learn some function to propagate the information through this graph neural network. And then an agent has some proper information to decide which configuration is the best to reach. And so, yeah, for sure now we're having these quite ambitious competitions that we run for 3.5 months. We have 2 tracks. So we'll be very happy if you can join us, take a look at it, and try to also participate or ask questions. And we have this first track about robustness. So you have these opponents that will attack your grid. So basically, at some point, you will see a line disconnected that you did not expect. So here is a link of the CodaLab competition. So if you want to see what such a competition looks like, actually, so yeah, basically here you're on the competition page where you will have some instructions about what to do, the rule of the game. You will have some leaderboard to see how the different participants are doing good with the problem. So yeah, take a look. We have this sandbox competition as well, which is a smaller problem that we had last year, so that you can also start more easily with such kind of problem. And so it's hosted on this CodaLab platform, which runs many other competitions as well. And so we have this other track about adaptability, where we change the amount of renewables in the energy mix from 1 times renewables to 3 times renewables. And the grid in which this track is actually running is actually the full IEEE 118 grid. So it will be interesting to see if some approaches manage to deal with those different energy mix, and it will be quite it will be quite a progress, you know, towards better AI models to apply it to power system operations, but also potentially grid development. And so, yeah, that's basically it for myself. So please join us, and we'll be very happy to see you there. And any kind of approach is welcome. So in a few months, we will have the results, and we can share it with everyone there. So thank you for listening.